Hello, my name is Matthew McKnight. I am a programming mentor with Team 4536, the minute box and millisecond box. And we're going to be looking at one of the programming core concepts called separation of concerns. One of the things I want you to learn as you go through this is not really how to write code, but how to think as a programmer. One of the main things that people have learned through a lot of blood and sweat and tears involves the concept of separating concerns within the code. We're going to talk about what that means. But separation of concerns is a core concept to object-oriented programming. So what is separation of concerns? Well, separation of concerns, put simply, is breaking the code into separate sections. And these separate sections are designed so that they are semi-independent, and each of them addresses what is called a concern. Each of them has their own concern. This means changing one section of code does not change any of the other sections if it's done well, because the code is not tightly coupled. Sometimes you'll have to do that, but generally you can avoid it. This is achieved in object-oriented programming, which Java is, by a thing called encapsulation. This creates modular code that is easier to maintain and is less prone to what I call bug migration, and that is when you make a change in one part of the code, it sneaks over and messes up another section. So we'll give a physical example. Stepping on the gas. You're in your car and you decide to step on the gas, and the result is that the engine RPMs go up. Now the pedal object and the engine object have different concerns. The pedal object's concern is setting what the RPMs should be. The more you step on the pedal, the higher the RPMs are going to be. The engine object, on the other hand, its concern is actually spinning the engine up to those RPMs. Those are distinct concerns, and each of these objects can focus on its own. So you have the pedal object and the engine object. Now here's the interesting thing about this. Let's say you're not driving a gasoline engine, as represented here. So when you step on the pedal, it actually is going to pass the information about the RPMs that are needed instead to an electric engine. Now the important thing to understand is the pedal doesn't care what the engine is. That is not its concern. Its concern is to determine what the RPMs should be. In fact, these two engines, to the pedal's viewpoint, are actually a single thing. It doesn't care what engine is sending the information to. That's not its concern. So when it actually steps on the gas, it tells the engine to rev. That's very nice and very separate. However, it's easy to make a mistake and not involve separation of concerns when you program. So let's talk a little bit about decoupling. If it's well written, it is loosely coupled. Trains are tightly coupled. What happens to one train car happens to all the train cars. That is great for trains, which have to go somewhere together, but unfortunately, tightly coupled is bad for code, because changes to any part of the code affect all of the code. You make a change in one part, it affects all the parts. And often you do not have control over what those other parts are. Loosely coupled code is better. Loosely coupled code means that changes to any part of the code only affect that part of the code. So you can work on the pedal and change it. You don't have to worry about affecting the engine, because each of them have their own concerns and they are not stuck together. So here's a good general rule when you're programming to kind of build loosely coupled code. Always pass data, never pass objects. And I'll explain what I mean by that. You'll notice the asterisk, by the way. That's because for every rule there's an exception. And if you're doing what is called dependency injection, the whole point of dependency injection is to pass the objects. So never pass objects, except in the case of dependency injection. That's an advanced feature we're not going to worry about. And to clarify, because I'm sure you're wondering, when I refer to data, I'm talking about the properties of things like strings or integers things that are not core to the identity of the object that you're working with. So data and objects can be passed in three primary ways into an object, or accessed from within an object. First of all, when an object is created or instantiated, you can pass it parameters. Parameters are the things that define the object, and one of the things you can pass in could be an object. Secondly, if the object has a property is something that an aspect of the object, such as car could have a color. If that object is a class, that means that anybody can reach into the object itself that you've created and muck with the inner workings, which generally you do not want. And thirdly, if you call a method is what an object can do, like a dog can fetch. If you call a method and you pass in a parameter which is an object, you are tightly coupling to that method because you're actually connecting it to the object you're passing in. And we'll look more at this. I'll give you a couple examples really quickly. But these are three ways by which objects can be interacted with between classes, and therefore damaging the whole concept of separation of concerns. When you pass information in to the instantiation or creation class or to a method, these are called parameters. They define what the method should do. For example, if you're going to rev the engine, it needs to know what the RPM should be. And these are necessary. So we're going to look at how we can actually pass parameters better to decouple. Again, we're only going to pass data. We're not going to pass objects. So here is an example of a class which has gaping holes in its encapsulation. And we're going to look at each of the things. At the very top is a property. The second line is the actual instantiation or creation code. And the third line, rev engine, is a method that the engine can do. So looking at each of these, we'll look at why these holes are open where they should not be. First of all, the property car spark plugs is an array of spark plugs, but it is a public property, which means anyone can access it. If I create an engine, I can go in after that and I can remove spark plugs or change spark plugs or set them to null. So I can break the engine, which if you're running the engine code, you do not want. This is not how you do separation of concern or how you protect your class. The second thing is the instantiation code is actually okay, apart from the fact that I put integer instead of int. This is limiting what is entering in. It is accepting data and not objects. And because it is accepting data, it is not going to be tightly coupled to whatever calls it. So this is actually acceptable code. We have successfully used encapsulation to allow separation of concerns. When it comes to rev engine, on the other hand, you'll notice that it's passing in an object called pedal. It's actually passing in the pedal object, so the engine can take the pedal object and examine it and figure out what the RPMs should be. That's exactly what you don't want to do. You do not want to pass in an object, because once you do, you have opened up a can of worms. Now pedal and engine are tightly linked, and any changes to one could affect the other. Plus, the separations of concerns doesn't happen here. So a better way to do it, you can see on the right. It's still the public class engine. People can create it, but there are some things to notice. First of all, the property car spark plugs is private. That means the only thing that can see it is the engine itself. No one can get in and muck with it. It is protected from the outside world, which is what we want. We've left the public engine font alone because that's totally fine. We're just accepting data there. That's what we want. And the rev engine command, the rev engine method, notice that it's no longer taking an object, it's taking data. An integer on the rotations per minute. And this is really important because right now it's a pedal calling the engine and telling what the RPMs are, but it could be a switch, it could be a dial, it could be anything at this point. The engine doesn't care. As long as it knows what its RPMs are going to be, it's going to be happy. And by loosely coupling, you enable that to move forward in a safe way. So I want to talk a little bit about encapsulation, give you a visual image of what you're doing when you encapsulate a class. We have the engine class. And what we're going to do in here, when we encapsulate it, is we're going to build a wall around the engine. We're going to build a big, big wall and not let anyone in. We are going to protect the engine class, which is great, except of course nobody can use it. So we're going to open up two doors. One is the instantiation code, engine, and the second is the method, rev engine. You can enter through those doors, but we have control over those doors. We'll tell you what you're going to bring in, and then we're going to examine it and decide if we like it. We're not going to let you mess with our engine. There's only two ways in. So this is an example of why that's important. Let's say somebody decides that they created an engine, and what they want to do is they want to really get the RPMs way up. They want the RPMs on this engine to be, I don't know, let's say 1 bajillion. That's a good number. They're going to start the engine, and they're going to set it to the RPMs of 1 bajillion. So they submit that as a parameter to the rev engine method. Oh, that's what happens. We have the ability to control that door. So if you send us a crazy number, we'll throw an error, or we'll reject it, or we'll simply set to the highest limit we want. Those are our choices, and we got to do it. And because we have encapsulated engine, we have kept it safe, which means it's much harder to break. So encapsulation logically breaks up your code. This is important. It helps you with coding to have it in chunks because then you know where to focus. It protects your classes from meddling kids, either accidental or intentional, as we saw with the bajillion RPMs. It allows a more modular approach to programming. Like I said, it could be a pedal, it could be a dial, it could be a switch. And because you have separation of concern, you're able to flip them around much more easily. And it simplifies what each class is responsible for, so you can think about the class itself in a simple and quick way. How are we going to use separation of concerns? Glad you asked that question. So here is an example of how we can make it happen. We're going to have three main areas, three main separations of where things work. The mode is the high-level command. This is what we want to do. Commands take that high-level command, that high-level order from mode, and then pass that down to the subcommand. So a mode will say, I want to do this, and in doing this, it will call on commands, and the commands will then go to the subsystem, which is the closest to the metal. In this case, the subsystems are the ones that deal with the actual motors in the drivetrain. Let's say in mode, we decide for our autonomous portion, we're going to drive in a square. And the command that we're going to use, there's two commands. One is drive forward in feet and turn in counterclockwise degrees. So those are the two commands that we're going to use to drive in a square. Now the subsystem itself is actually really simple because it's just running some motors for the drivetrain. So it's basically got one method, drive. And the drive is going to take a double, which is a decimal, motor in feet, decimal of left motor in feet. Each of the two different motors will be that far forward, and they can be different numbers, which will enable it to turn or to go forward. So drive in a square, we're going to set it to 5.0, so it's going to go forward 5 feet, and it's true, which means that it's going to be moving in a clockwise direction. That means the commands we're going to need are drive forward 5, turn negative 90, drive forward 5, turn negative 90, drive forward 5. You get the idea, 4 times in a row. Now the command itself is then going to go to the bare metal and tell it what to do. The mode doesn't care about the subsystem. It just tells the command what to do and the command does it. So the command is going to turn to the subsystem and it's going to do something like drive 5, 5, drive negative 0.25, positive 0.25, which will turn it. Not sure it'll be 90 degrees, but that's just a quick example. That is the command it's going to pass to the subsystem. Now, this may seem like a lot of work, but by breaking it up in this way, it gives us flexibility to change things and to test things. For example, what if instead of drive in a square, we decide to drive in an equilateral triangle of 5 feet? Well, it'd be very similar with a few minor tweaks to the code, but it'd be really, really easy to code from this point. So what we're going to do in our next video, hopefully, is we're actually going to create that code. We're going to create code so that it can drive in a 5-foot square. And then we'll see if it works. So we'll see you next time.